Drawing the atomic structures of complex compounds with bonds is difficult. To overcome this, Lewis established an easy way to represent bonds within molecules and ions. He created it as per the shared pair of electrons and the octet rule. In his method, electrons are drawn as dots and the bonding of a pair of electrons is represented by a line. Therefore, it is also known as the electron dot structure. The Lewis structure for an atom is the chemical symbol for the atom, surrounded by as many number of dots as the number of valence electrons in it. For an ion of an element, we first need to draw the chemical symbol for the element surrounded by the number of valence electrons present in the ion. Then, the whole structure is placed within square brackets, with the superscript indicating the charge on the ion. The charge of the ion is the number of electrons gained or lost. To draw the Lewis structure for a molecule, first draw the atoms and join them with lines so that for each atom, the total number of valence electrons becomes 8. To draw the Lewis structure for compounds, first, the unit of the negative or positive charge should be deducted from the total number of valence electrons of the compound. The remaining number of valence electrons should be distributed as the bonding pairs of electrons. For example, a carbonate ion has 2 negatively charged units. The number of valence electrons in a carbonate ion is the sum of valence electrons of 3 oxygen atoms and the valence electrons of the carbon atom. That is 22. Therefore, the number of electrons to be distributed in a carbonate ion will be 22 minus negative 2, that is 24. In the Lewis structure, the least electronegative atom occupies the central position, which is carbon here. Now, when 24 electrons are distributed among 3 oxygen and 1 carbon atoms, it looks like this. After assigning electrons, the remaining electrons are utilized for multiple bonds or remain as lone pairs. We will replace each pair of bonded electrons with a line. Notice that the total number of valence electrons becomes 8 for each atom. With the sharing of valence electrons for the full octet in each atom, the Lewis structure involves the octet rule. However, there are some molecules in nature that do not follow the octet rule. In some molecules, the number of electrons surrounding the central atom is less than 8. For example, beryllium hydride and boron trichloride have 2 and 3 pairs of electrons respectively surrounding the central atom. In molecules with an odd number of electrons, such as nitric oxide, the octet rule is not satisfied. The octet rule also does not apply to the molecules with expanded octets. Though the octet rule is based on the inertness of noble gases, some noble gases, such as xenon and krypton, react with other elements and form compounds. The octet theory also does not explain the shapes of molecules and energies of orbitals. However, the molecules that do not follow the octet rule can still be represented by the Lewis electron dot structure. Therefore, though the Lewis structure involves the octet rule, it is not limited to the octet rule. However, in case of polyatomic molecules, there can be more than one possible Lewis structures for a molecule. To determine the best possible Lewis structure for a molecule, we need to find out the structure with the lowest energy from a number of possible Lewis structures. The lowest energy structure is the structure with the smallest formal charge on the atom. Formal charge is the charge assigned to an atom in a molecule, assuming that electrons are shared equally between atoms in a chemical bond. For the correct Lewis structure, it should be other than 0. The formal charge can be expressed as the difference between the number of electrons present in that atom in its isolated state and the number of electrons assigned to the atom in the Lewis structure. For example, in a phosphine molecule, the number of valence electrons in the phosphorus atom is 5, and the number of lone pairs is 2. There are 6 shared electrons among 3 hydrogen atoms and 1 phosphorus atom. Therefore, the formal charge is 5 minus 2, minus half of 6, which is 3. This gives us the formal charge as 0. The Lewis structure and formal charges are applicable only to the molecules formed by covalent bonding. Let's understand what a covalent bond is. In 1919, with the help of Lewis postulates, Langmuir brought in the term covalent bond to define a bonding pattern where the electrons are not transferred. In covalent bonding, atoms share electrons so that the number of valence electrons in each atom becomes 8. For hydrogen, it is 2. Here, the nuclei of both the atoms keep attracting the shared electrons and do not give away any electron completely, unlike ionic bonding. For example, in a water molecule, one oxygen atom shares valence electrons with 2 hydrogen atoms. In this way, the valence electrons in an oxygen atom will be 8, and thus, oxygen gets the stable status of its nearest noble gas, neon. On the other hand, by sharing 1 electron of oxygen each, the hydrogen atoms will have 2 valence electrons each. It will get the configuration of helium. When 2 atoms share 1 electron pair, they form a single covalent bond. For example, the fluorine molecule. When 2 atoms share more than 1 electron pair, they form multiple bonds. In the ethylene molecule, the 2 carbon atoms share 2 pairs of electrons and a double bond is formed between the 2 atoms. Nitrogen molecules form triple bonds. The factors that affect chemical bonds are known as bond parameters. Some such factors are bond length, bond order, bond angle, and bond enthalpy. Let's look at each of these factors. Bond length is the distance between the nuclei of the atoms that are bonded together. It is directly related to the radius of each atom in the bonded pair. In a covalent bond, the radius of each atom forming the bond is called the covalent radius of the atom. In a molecule containing similar atoms, the size of the atoms is the same. Hence, their radii will be the same. In such cases, the covalent radius is half the internuclear distance between the bonded atoms. Another type of radii between atoms is the van der Waals radius. It was calculated by van der Waals and provides the overall size of an atom, including its non-bounded valence shell. It is given as half the distance between two similar atoms in separate molecules in a solid. Some of the methods used to measure bond lengths are spectroscopy, X-ray diffraction, and electron diffraction. The bond length between carbon atoms in an ethane molecule is calculated to be 1.54 angstrom units. The carbon-to-carbon bond length in ethylene is 1.33 angstrom units, while in acetylene it is 1.20 angstrom units. This difference in bond length leads us to our next parameter, bond order. The number of chemical bonds between a pair of atoms in a molecule is called the bond order of the molecule. Bond orders can be calculated from Lewis structures. For example, in ethane, two carbon atoms share one pair of electrons. Therefore, the bond order is said to be 1. In ethylene, two carbon atoms share two pairs of electrons. Therefore, the bond order is said to be 2. And in acetylene, two carbon atoms share 3 pairs of electrons. Therefore, the bond order is said to be 3. Now, if you observe the bond order and the bond length of these molecules together, you will notice that they are inversely proportional to each other. This is because as the number of shared pairs of electron goes on increasing, the distance between the two nuclei forming the bonds goes on decreasing. From the Lewis dot structure, we get the sequence of atoms in a molecule. But what about its structure? For this, we need to look at the next bond parameter, bond angle. It helps us create a three-dimensional structure of the molecule around the central atom. In a molecule, the angle between the orbitals present around the central atom is called the bond angle. In a methane molecule, there are 1 carbon and 4 hydrogen atoms. The bond angle of methane is 109 degrees and 28 minutes. It means that the angle between any two bonds that are formed between a carbon atom and the hydrogen atoms is 109 degrees and 28 minutes. Usually, when the bond angle is 90 degrees, the shape of the molecule is octahedral. When the bond angle is 180 degrees, the shape of the molecule is linear. Similarly, when the bond angle is 120 degrees, the shape of molecule is trigonal planar. Bond angles are measured using spectroscopic methods. Another bond parameter, bond enthalpy, is defined as the amount of energy required to break one chemical bond between two gaseous atoms in a molecule. It is expressed in kilojoules per mole. For example, the energy required to break the bond between the two atoms of a hydrogen molecule is 435.8 kilojoules per mole. When a molecule is made of more than two atoms, it consists of more than one bond. In such cases, the bond enthalpy for each bond may be different. Hence, the average of all the bond enthalpies is taken as the bond enthalpy of that molecule. Bond enthalpy is inversely proportional to bond length. This means the shorter a bond between two atoms, the more energy it takes to break it. We have already learned how to write the Lewis structures for different molecules and ions. For certain molecules and ions, more than one Lewis structure is possible. For example, consider the following possible Lewis structures for an ozone molecule. These are the two structures possible. In both the structures, one oxygen-oxygen single bond and one oxygen-oxygen double bond is present. These two structures imply that one bond is shorter than the other. The normal bond lengths of oxygen-oxygen single bond and one oxygen-oxygen double bond are 148 picometers and 121 picometers respectively. But experimentally, it is determined that the bond length between any two oxygen atoms in ozone molecule is the same, which is equal to 128 picometers. This implies that the bond length between the oxygen atoms in ozone molecule is intermediate between oxygen-oxygen single bond and oxygen-oxygen double bond. It means that all the bonds in ozone molecule are equivalent. Therefore, neither structure 1 nor structure 2 explains the observed bond length. It is observed that for certain molecules, one Lewis structure cannot explain all the observed parameters such as bond length, bond strength, and so on. Therefore, more than one Lewis structure is required to explain all the observed parameters, as a single Lewis structure is inadequate to represent the molecule accurately. If a molecule that can be represented by two or more structures which differ only in the arrangement of electrons, then the molecule is said to be in resonance, and the set of several possible structures are called resonance structures or canonical structures or canonical forms. Any two resonating structures are represented by inserting a double-headed arrow between them. It is important to note that there is no equilibrium between the canonical forms. All the canonical structures have similar energy and the same arrangement of atomic nuclei, but differ in the arrangement of electrons. However, the molecule never actually has the structure of any of the canonical forms at any point of time. The actual structure of a molecule is a hybrid of all resonance structures possible. It is called a resonance hybrid. This resonance hybrid is more stable than any of the contributing resonating structures. In this example, the resultant of these two structures, that is, the resonance hybrid, explains the equivalent nature of the bonds and the observed bond length, which is 128 picometers as shown here. Let us reinforce this concept by considering the possible Lewis structures of a carbon dioxide molecule and polyatomic nitrate ion respectively. We can represent a carbon dioxide molecule by the three following Lewis structures. None of the single structures explain the observed carbon-to-oxygen bond length, which is 115 picometers. The magnitude of this bond length is found to be intermediate between the bond lengths of a normal carbon-to-oxygen double bond, which is 121 picometers, and carbon-to-oxygen triple bond, which is 110 picometers. Hence, the resonance hybrid of these structures, as shown here, explains the experimentally determined bond length. Similarly, we can represent the nitrate ion by the three following Lewis structures. In each structure, there is one nitrogen-oxygen double bond and two nitrogen-oxygen single bonds. However, experimental studies reveal that all nitrogen and oxygen bonds are found to be equivalent. Hence, the resonance hybrid of these three structures depicts the equivalent nature of nitrogen-oxygen bonds. Therefore, the nitrate ion is best described as a resonance hybrid of the three possible canonical forms as shown here. Thus, we can conclude that resonance stabilizes the molecule as the energy of the resonance hybrid is less than any of the canonical structures. Also, a molecule can have only a single structure, that is, the resonance hybrid of all the canonical forms.